250 million years ago, sudden releases of methane produced kind of a secondary effect that finished off large chunks of life on Earth. And one of the debates right now is whether the methane that is buried in the Arctic, whether the methane that is, in the permafrost, in the seas all over the world, how rapidly that will be mobilized and how destructive that mobilization will be.
The release of this ancient methane may lead to exponentially more warming. Will this methane create an apocalyptic scenario? This is a question scientists are desperately trying to answer.
I'm the director of the Center for Gas Hydrate, Environment and Climate. Here we have a team of 50 to 60 scientists working on understanding the impact of methane on the global climate system. This methane is stored beneath the Arctic Ocean floor in huge reservoirs at locations we sometimes know, but we often do not know very much about it. So we are applying here geophysical methods to quantify the methane hydrate reservoirs and also to see how stable those methane hydrates are today, but also in the future. Methane is one of the most aggressive greenhouse gases. Methane has, fortunately, a shorter lifetime. The Earth has a natural system for regulating input of methane from the ocean and into the atmosphere. And this system is working quite efficiently. But this system is also changing because the ocean current system is changing, the ocean temperature is changing, the ocean chemistry is changing. So methane was in a kind of equilibrium for some time. And during the last couple of years, we see quite a distinct increase in methane. Do not know where this signal is coming from. And at the present time, that, of course, is putting a pressure on the scientific community to give an answer to the politicians. What is going on with the methane in the atmosphere? Where is the methane coming from? What is presently becoming more unstable?
We have done some very comprehensive measurement campaigns where we have measured at the seafloor, in the ocean, at the sea surface and in the air at the same time to understand how methane is regulated in this whole system. There is a lot of methane stored at the seafloor, and this is so much that only a small change might impact the ocean or the atmosphere. The balance here needs a lot more focus, a lot more observations, and combining atmosphere, ocean, climate, different kind of competence together.
In my profession, I'm interested in studying methane cold seeps in the ocean, in the Russian Arctic and also in the Barents Sea. It's, well, basically streams of gas bubbles rising from the seafloor, and those gas bubbles are mostly composed of methane gas. First, it's gas hydrates, that's solid form. It's basically ice-like structures. Also, the gas can be present as free gas, which is gas bubbles. Plumes of methane bubbles can vary. In some areas in the Arctic, we find gas seeps as tall as 800-900 meters. And the water depth in these areas is a little more than 1,200 meters. In shallower areas, we often find gas seeps that are almost reaching the sea surface. East Siberian Sea is definitely an area of concern for guys studying methane, in particular because it's so shallow there. So those methane bubbles have really high potential to get to the sea surface. Some areas, Spitsbergen, we find methane flares that are almost reaching the sea surface.
We have warmed the atmosphere to such a degree that we have hit the tipping point of a melting Arctic. We now face the potential for an abrupt climate change scenario. Current models predict we will shoot way past the Paris Agreement to 5 degrees and more, causing even more catastrophic tipping points to be activated.
Warming might lead to large injections of methane into the atmosphere. It's something we need to be concerned about. I would only add that it's one of many possible stressors. move into a high-risk situation where we don't really have any experience. We don't know how to deal with it.
Permafrost and methane in general is of a great concern. And I think that this is something perhaps we need to pay more attention to methane in general in relation to the climate issue. My concerns are that there are great reservoirs of methane in the world, in particular in the Arctic. It is the risk of going beyond a tipping point where it will be difficult to go back and reverse the problem.
It's a very plausible feedback mechanism that in Arctic soils, permafrost soils, there's an enormous amount of organic material frozen, and the amount that is available there potentially to turn into CO2 and methane is maybe 3 times, 4 times all of the fossil fuels that we have burned. If we take all this material out of the deep freeze, you very likely get large CO2 and methane emissions on a huge scale over which we have no control.
I study methane emissions from lakes. We are in interior Alaska, and we are in discontinuous permafrost. The thing that we're looking at is microbial methane. This methane bubbling here behind me, it's dead plant and animal remains that were locked up in permafrost for tens of thousands of years. And as that permafrost is thawing, the microbes eat that soil carbon and they turn it into methane. This process of permafrost thawing and that thawing permafrost fueling methane production, and then methane escapes into the atmosphere, causes climate warming, which causes more permafrost to thaw. We call that a permafrost carbon feedback. It is a natural process. Our concern, though, is that as climate warms at a faster rate than it has in the last 10,000 years, that permafrost is going to respond by thawing a lot more quickly and releasing at a faster rate methane gas. Now, every time I go to a new lake, I attempt to light these gas pockets because it's a very high concentration of methane. It's highly flammable. We see a positive flame test when they contain methane. So it's a quick gas chromatograph on the lake to tell us, do we have a methane lake or are we dealing with a different kind of lake? There are many new lakes forming that were not here 30 or 60 years ago. And those lakes have 10 to 100 to 1,000 times more methane than the rest of the lakes. They are a picture of the type of methane emissions we expect to see in the next 10 to 50 years as permafrost warms and thaws, and that permafrost feedback cycle kicks in and really accelerates.
Now, is it methane? Is it permafrost? Is it the dissolved organic carbon in the ocean, which is suddenly remobilized? These things are all intertwined with each other. So really what one needs to ask is, are there positive feedbacks within the system? The answer is yes. So it just stands to reason, purely by common sense, the less you disturb it, the better off things will be.
We have the solutions at hand, but the question still remains. Can we mobilize and take collective action before it's too late?
There isn't the oomph in the world to do this. They talk about, with the Paris Agreement, how we must reduce our carbon emissions and to keep temperature rise at some low level. But in fact, of course, we won't be able to do that. The technology that can save us is something that will take carbon dioxide out of the atmosphere. So it ought to be obvious that the biggest research effort that man is involved in should be to develop direct air capture methods that work. And if we do that, then we can save the world. And so why don't we do it?
Direct air capture is machines which take in ambient air and extract the CO2 from this air. For the last 10 years, we have been working on direct air capture with the goal of making it with the least possible energy impact and ultimately with the best economics. This machine consists of 4 40-foot shipping containers and can be any size. There is no limit to it. So we take in the ambient air here, and inside we have our filter structure. We get the waste heat of the waste incinerator to drive this plant. Once the CO2 is captured, this gas is then going to a greenhouse, and this greenhouse is using the CO2 to increase the CO2 concentration in the atmosphere of the greenhouse, which is done already nowadays, but with fossil CO2, and from tomorrow on, they're going to use atmospheric CO2. This plant will allow to close a carbon cycle. So of course, the CO2 goes into the greenhouse and goes to the tomatoes and cucumbers. And once we eat them, the CO2 goes back to the atmosphere. But since we recapture the CO2 from the atmosphere, it's a closed cycle. So this can be a missing piece of the pie in order to close a global carbon cycle in the energy or transportation sector. So besides using CO2 in a greenhouse like this, we can take CO2, we can take water, and we can take renewable energy. We can again produce fuels, for example, jet fuel. In order to capture 1% of global CO2 emissions, we would need roughly 300,000 of the plants behind me, which is of course a very high number. But if you compare this to existing infrastructures, it's a scale which humanity can handle. So it's definitely an achievable goal. The next project is to bring a plant to Iceland to capture CO2 from the air and sequester the CO2 underground. And in 2 hours, you literally turn CO2 into a stone, which stores it in a permanent and safe manner. In order to run the plant, we would use geothermal heat. There's an abundance of it on Iceland. Therefore, we would have low carbon footprint energy available to drive the machine.
So today is a very special day. We have brought CO2 capture plant up here to Iceland. And we are taking CO2 out of the air and then pumping it underground, storing it in the basalt rock formation within the Carbfix project. So we extract CO2 from the air and permanently remove it by turning it into rock. And yesterday night was the first time that atmospheric CO2 was injected into the ground. We can go up to thousands, 10,000, 100,000, and even up to millions of tons of CO2 per year that can be extracted from the atmosphere. That is actually, to our knowledge, the first time ever in the world that direct air capture of CO2 has been combined with underground safe and permanent storage of CO2.
Yeah, it's a new relationship with carbon. Why can't we find a way to make it an ingredient for something? Why can't we put it in our plastics or in our building materials? Or through the help of carbon dioxide chemistry, turning carbon dioxide into the things that we need every day?
I'm Daniel Nocera, the Patterson Rockwood Professor of Energy at Harvard University. These are my labs, the labs where we invented the artificial leaf and the bionic leaf. And what they do is a complete photosynthesis, sunlight, air, and water to fuels and food. Think about photosynthesis. If you think about what it really does, is the building block of life, and its building blocks literally are CO2, water, and sunlight. And we build all of this, like this, wood and food and starch and biomass. That's a remarkable transformation. This photosynthetic process, it's very complex, but we really listen to nature. And that we finally ended up doing in 30 years. And something that makes us really happy, not only can I say, yes, we can do it artificially, I can do it 10 times better than photosynthesis. We made special catalysts that coated the artificial leaf, and then they would split water to hydrogen and oxygen. The second part of the invention is the bionic leaf. It takes the hydrogen from the bacteria, and then it makes fuels. And so depending on what genes I put into the bacteria, I could have the bacteria make materials, they could make drugs. We've shown they can make fertilizer. We can work out of any water source, including natural waters, seawater. As long as you have my artificial leaf, you can do it in your backyard. We don't need to dig what's been down there and release more CO2. The artificial leaf, working with the bionic leaf, takes the CO2 out of the atmosphere, uses sunlight and water, and we make fuel. So we don't add any more to the atmosphere, any more CO2. And it's another issue because the cost I'm up against, the developed world has spent tens of trillions of dollars to build what they now use. It's kind of hard to walk away from a multi-trillion-dollar investment that you've paid off. So that's what it's all about. Therefore, you need policy and you need good partnership. And the public informing them that they have options and that there can be this different world.
This new world can be sustainable, innovative, and profitable. The green economy is creating millions of jobs and will create millions more. It matches and will surpass the economy of the fossil fuel industry. The challenge to reverse climate disruption opens up opportunity for everyone. It is now more profitable than ever to be green.
Up until recently, the profit you could make from creating the problem was greater than the profit you could make from the solutions. So the solutions had to be done with subsidies, which were rare, non-existent, or altruism, or faith. But people who were making the problems were raking it in, raking it in, raking it in. And I think we're at a crossover where actually the profit you can make from the solutions is greater than the profit from the problems. And that is not well understood. So it's not that altruism need not apply, it's a great thing, but actually altruism will not be needed in order to move towards a world where we reverse global warming because, in fact, it's less expensive. It's more profitable, more beneficial, more jobs. It's the most amazing thing that's happened in the last few years and is going to do nothing but increase as the years go by because engineers and designers and basically who are unknown and unnamed have been working diligently and are working diligently to reinvent a new way of being a human being relating to this planet.
In Orkney, we have a really strong maritime tradition, and since the 70s, the oil and gas industry in Aberdeen has been a major contributor to the local economy, providing tens and thousands of jobs. But really, in the last few years, we've seen quite a big downturn in terms of the oil and gas industry and the price of oil. But we've got lots of really experienced people in offshore operations on our doorstep, and they're finding new jobs in offshore renewables and companies such as ourselves. Tidal energy is almost an entirely untapped resource. We think we have the potential around the world for about 100 gigawatts of capacity, perhaps more. And what that equates to is low carbon energy for millions and millions of homes. What we've got here is the world's most powerful floating tidal energy generator. We've got a floating platform to which 2 rotors are mounted.
We start with the rotors turning, which produces the electricity, which comes back up into the machine where it's conditioned, and then it gets transformed and stepped up and fed back into the grid.
It's like a wind turbine on its side with 2 rotors instead of 1.
2 weeks ago, we had great success. First period of 24-hour continuous generation from the device, it actually operated beyond expectations. The device itself generated over 18 megawatt hours of power in that 24-hour period. We're converging on more traditional methods of renewable generation and really putting tidal out there as a real competitive technology across the world and the world's generation needs.
The tidal turbine it's 63 meters long in total. We do all the power conversion within the device itself, and it's ready then for export right into the UK electricity grid. So we're aiming for tens of thousands of these tidal turbines. We've got this fully integrated system for producing low carbon energy, so we're very excited about it.
So EMEC was set up as a testing laboratory because we know that there's a huge amount of energy in the oceans all around the world, and we're trying to find a way to harvest it. And so we realized that one of the most important things was to have a test center which would allow us to find out how to do this properly. And so what we've got is a site here where we've got cables that are out in the sea that allow developers of these machines to put these machines onto our cables, and the electricity is then brought onto shore, and that then feeds into our national grid. So this is real. This is making electricity out of seawater. So at the moment, we've got a device called the Penguin, and that's by a company called Wello Oy, and their machine is effectively a large pendulum inside a ship, and as the ship moves, so this pendulum turns horizontally, and that then generates electricity. The sea is unrelenting, and it will really try and damage equipment. So making equipment that's reliable, robust, efficient, cost-effective, all these things are the things that people are grappling with. But the really clever thing is we have done that piece of alchemy. We've actually turned seawater into electricity. And that really is huge, because people have worried about whether you can do this or not for years, and we've just shown you can. And that's a big step forward.
No one can say that the scientist has not warned, has not told that we have to reduce the emissions of greenhouse gases. That should be clear to many.
How much farther can we go? How many more tipping points can we go before we hit a tipping point from which our civilization cannot recover, or from which the life of this planet, or a large portion of the life of this planet, cannot recover? We cannot allow ourselves to reach those points, and we're so damn close to it.
We're at a turning point. Either we can stay the course and drown, burn, and starve ourselves to death in the face of the climate crisis, or we can come together, we can innovate.
Where do we stand? Is it possible? Is it game over? Or is it, in fact, game on, which is that we have at hand the ability, capacity, and solutions that can reverse global warming, not mitigate, not reduce, not stabilize, but reverse. When you make your goals bigger, it opens up possibility. It opens up imagination. It opens up innovation. It doesn't foreclose, it actually does the opposite. And so it's not that there's one solution, but together, you can achieve drawdown by doing 80% of the solutions. Every one of them has so many cascading benefits, makes a better world for everybody. So we don't lose by understanding that climate change is happening and responding to it. So what's the problem?
We are the first generation to see the advance of climate disruption and the last with a chance to fix it. In spite of all this evidence, we are currently burning fossil fuels at an ever-increasing rate. We have heard from the scientists who have told us the truth based on actual research. It is time to end the delay, to listen, and to implement the solutions at hand. Time is running out. The ice is melting. Decisive action must be taken now. There is no other option. This moment is within our reach. Let us grasp it. It is up to us, each one of us, to save this unique blue planet for generations to come.